In introductory circuit courses, or in Physics 2, we investigate the treatment of simple combinations of resistors. When we speak of equivalent resistances, we are imagining combining two or more resistors and replacing them with a single resistor. This new resistor is represented by R with a subscript of two parallel lines. We pronounce this as R parallel. One of the main reasons that we do this is so that we can determine the current, resistance, and power within a simple circuit. We'll look at this in a later lesson. For now, we are going to just combine some resistors and not worry about the rest of the circuit. I've talked about this in another video, but let's remind ourselves of the difference between parallel and series combinations. Parallel combinations give charges multiple ways to get from point A to point B. Series connections, on the other hand, give charges only one way to get from point A to point B. Resistances connected in parallel act as reciprocals. I've made another video to explain this, but for now we will just apply the equation. Here we have three resistors connected in parallel. The equation for combining them is given by the fraction 1 over R parallel equals the fraction 1 over R1 plus the fraction 1 over R2 plus the fraction 1 over R3. If you have two resistors, only use two terms. If you have more, use as many terms as you have resistors. Note that the equation is solved for the reciprocal of R parallel. Don't forget to make sure that this is solved for R parallel by the end of the problem. This is a common mistake that people make. To calculate the resistance for two parallel resistors, we'll start with the proper equation. The fraction 1 over R parallel equals the fraction 1 over R1 plus the fraction 1 over R2. For this type of an equation, we'll find the common denominator by simply multiplying each denominator by the other. This gives us a denominator of R1 times R2. Don't worry about trying to find the least common denominator. This gives us 1 over R parallel equals the fraction R2 over the denominator R1 times R2 plus the fraction R1 over the denominator R1 times R2. Note that each fraction was multiplied by a fraction with the other resistance over itself. R1 over R1 is just 1, so the value of each fraction hasn't changed. Now that we have the same denominator for each, we can simply add the numerators. This gives us 1 over R parallel equals the quantity R1 plus R2 over the common denominator of R1 times R2. Since up until this point the left side of the equation is 1 over the equivalent parallel resistance, we need to take the inverse of each side. Since each side is a fraction, we can just flip over each side. This gives us R parallel equals the fraction R1 times R2 over the quantity R1 plus R2. Note that we cannot just flip everything over until we have a single fraction on each side. Now you could learn the equation in this form, but it makes it a bit harder to know what to do if there are more than two resistors. This bit of algebra should be easy for you to do when needed. Now let's do an example. Suppose that a 330 ohm resistor and a 220 ohm resistor are connected in parallel. We want to know what the equivalent resistance of the combination is. I'm going to treat these two numbers as having three significant digits. We could show this with lines over the zeros, but that can be tricky to implement in PowerPoint. From the problem, we can set R1 as 330 ohms and R2 as 220 ohms. We need to find the equivalent resistance R parallel. I like to draw a quick sketch of the circuit as well. We'll start out by writing down the parallel resistance equation. Since we just did the algebra on this, I'll just show it quickly. We end up with the equation R parallel equals the fraction R1 times R2 over the quantity R1 plus R2. Due to the lack of space, I'm just going to write this again at the top of the page. Next, we put in the values for each variable. This gives us R parallel equals the quantity 330 ohms times 220 ohms divided by the quantity 330 ohms plus 220 ohms. We could put this directly into our calculator, but I like to show the intermediate steps. Calculating the numerator, we find 72,600 ohms times ohms. Calculating the denominator, we find 550 ohms. Notice that one of the ohms in the numerator cancels out the ohms on the bottom. The fact that this leaves us with units of ohms is a good sign that we have done our algebra correctly. Dividing the two numbers, we arrive at an equivalent resistance of 132 ohms. I like to circle my final result. Since my final answer only had 3 digits, I didn't need to round to fix for significant digits. If you don't mind, a like at this point would help me know that you're finding this information helpful. I grew up using a calculator that only showed one value at a time. Because of this, I tend to do each step separately. With modern calculators, you have multi-line inputs, so you might not want or need to show all of the calculations. I like to use the Desmos scientific calculator at desmos.com/scientific. For my numerator, I just multiplied 330 times 220 to get 72,600. For the denominator, I just added 330 plus 220 to get 550. If I wrote each of these down, I'd divide them and write down my final result. Since the result was just 3 digits, I can write it down as is. If I ended up with more than 3 digits, I'd write down a few extra, then rewrite the answer with only 3 significant digits. Writing down each of the steps helps you find any potential mistakes more easily. When checking your work, you can check each step. Since the calculator allows me to do multiple steps at once, I can simply enter everything, then hit enter to get my result. Notice that the step where I wrote in my numerical values gives me the exact numbers in form to enter, except for the units. That's why I always recommend that you do the algebra first, then write out the numbers. Then enter it into your calculator. You're less likely to make a mistake this way. In my next video, I'll show you how to add 3 resistors in parallel.